In question number 9.97, the details are as follows. There is a railroad car, and in that car stands a boy, and the total mass of the boy and the car is given to be m. Now the boy holds a ball in his hand, and the mass of the ball is given to be small m, and the system is initially at rest. Now it is given that the boy throws the ball with a velocity v0 towards the right, and we are going to assume that this velocity v0 is in the ground frame. So naturally, when the ball is thrown with this velocity towards the right, the car and the boy are going to travel towards the left by the law of conservation of momentum. It is also to be noted that there is no friction from the tracks on the wheels, and this fact will be important in deciding how the car travels after the ball is thrown. So I just draw the fresh diagram in which I have this car and the boy is still standing in the same position like that, but the only thing is the ball has left his hand and it is traveling in the ground frame with a velocity v0 towards the right, and the mass of the ball is m. Now we know that the car will travel towards the left, but if I want to adopt the notation or the convention given in the solution in the book, then in that particular solution it has been assumed that the car and the boy inside travel towards the right with a velocity capital V. It doesn't matter, finally V will turn out to be negative. So to find the value of V, you apply momentum conservation in the horizontal direction. Remember that during the throw there is no net horizontal external force acting on the system because there is no friction from the bottom, that is from the track on the wheels. So the momentum initially of the system in this picture was equal to 0, and the momentum in this direction, let's take rightward as positive, is m times v0, and remember the car and the passenger, the boy, have a total mass of m, so their momentum must be m into v, and this actually gives me the value of v to be minus m v0 divided by capital M, and the minus sign is of course expected. And so the car will be traveling towards the left with a velocity equal to m v0 upon capital M, and this will happen, or this state will continue until the ball hits the right hand side wall of the car. That's when the second collision, or that's when a collision, the first collision in fact, will occur. And we now have to find what is this time interval before that collision, that is between the throw and the collision with the right hand side wall. Now if you go back to the picture, you see that the ball has to, you can go, or you can analyze the picture in the reference frame of the car itself. So in the reference frame of the car, from the reference frame of the ground, the car is coming towards the left with a velocity m v0 upon capital M. And now if I go to the reference frame of the car, then of course the ball is approaching the right hand side wall with a speed of, I have to subtract the velocities, but they are oppositely directed, so effectively I add them, mv0 plus, it's going to be v0 plus mv0 upon M, and that is the relative velocity of the ball in the reference frame of the car. Now we have to find the time interval required for the collision to take place, and you know that the ball, I want the time interval, the the ball, you can solve it in the reference frame of the car itself. The ball is going to travel a distance L, and it's going to go at a constant speed of v0 plus mv0 upon m. So I'll take v0 common into 1 plus m upon m, and this is the time interval between the throw of the ball and the collision with the right hand end of the car. And for all this time the car is traveling towards the left with the velocity which we have just calculated. And this condition, of course, the situation is going to change once the collision occurs, but we are still to analyze that. So it means that the velocity of the car is what is it, mv0 upon capital M towards the left. That's how the car moves for a time interval 0 less than t less than, and the collision occurs at a time L upon 1 plus m upon capital M multiplied by v0. So that's the explanation of the first part of the solution. Now after the collision occurs, we can find out what are the new velocities of the ball and the car. So we'll just analyze the collision. What's going to happen is there is this mass small m which is traveling with a velocity v0, and there is this capital M which has a leftward velocity actually, but we have stated the velocity to be negative in the rightward direction. So v is minus m into v0 upon capital M. So I will still adopt the convention of rightward positive, and I want to find out what are the two velocities after the collision, and I will call them v ball and v car. So these are the velocities of the ball and the car immediately after the collision. And how do I find these velocities? I first, as usual, apply the momentum conservation. So mass of these are some fireworks which you just heard. They are going on outside, so please ignore them. Now the mass of the ball multiplied by the velocity of the ball after the collision plus the mass of the car and the boy multiplied by v car, that's after the collision, immediately after the collision, that's equal to the original momentum of the system. We have already calculated it to be 0. We know it's 0. So that's going to be the conservation of momentum in the horizontal direction. That's equation number 1. And also we have been told that the collision is an elastic collision. So that means that the speed of approach and the speed of impact in this case, the speed of approach and the speed of separation in this case must be the same. So they are approaching each other with a speed of v0. I hope you follow what I'm saying. E is the coefficient of restitution. It's equal to 1 for an elastic collision, and that's the modulus of the velocity of separation upon the modulus of the velocity of approach, etc. So the speed at which they are approaching each other must equal the speed at which they separate. Speed at which they are approaching, already calculated, the relative speed is v0 plus m v0 divided by capital M. That's the speed at which they are approaching each other, and the speed at which they will separate from each other is going to be v car minus v ball. That's going to be my second equation. But just I'll explain something. How come you know it's v car minus v ball and not v ball minus v car? So it's very simple actually. The coefficient of restitution, we have already defined it as follows. The relative speed of separation upon approach. So supposing I take v car minus v ball in the numerator, then in the denominator I have to invert the terms. I must take the initial velocity of the ball minus the initial velocity of the car, and the initial velocity of the ball was v0, and the initial, well, minus the initial velocity of the car was minus m v0 divided by capital M, and this is equal to 1 because it's a perfectly elastic collision, and that's why I get v0 plus m v0 upon capital M is equal to v car minus v ball. Actually that's the correct procedure to get this particular equation, otherwise there will always be this confusion whether to have v ball minus v car or the reverse on the right hand side. Now if I solve these two equations for the two unknowns v ball and v car, you can do that yourself. You get v ball is equal to minus v naught. In other words, it means that in the ground frame the velocity of the ball has just reversed, and you also get v car is equal to m times v naught divided by capital M. So the sign which was minus has become plus. It means that the velocity of the car has also just reversed in sign. Now it's better to work this out using equation number 1 and equation number 2, I think, rather than remembering any general result. And now we can easily find what is the further time interval delta t before the second collision occurs. So remember, if you go to this picture, what's going to happen is this ball in the second picture, the ball is going to travel and it's going to hit, it's going to hit the left hand side wall, and for all that time, this time interval between the first collision and the second collision, the car is traveling at a constant velocity. So what is that time interval? So delta t is going to be, again the ball has to travel a distance L in the reference frame of the car. So we are going to divide the distance it has to travel by the speed at which it is traveling, and both are in the reference frame of the car. So the ball covers a distance L in the car frame divided by the relative speed. Of course I have to subtract these, so once again it's going to be mv naught upon capital M plus v naught. So L upon v naught into 1 plus m upon capital M. Now this time interval is the same time interval that we got before the first collision, that is between the throw and the first collision. So I get the same time interval between the first and the second collisions, and what that will mean is the following. I'll just rub this out. It will mean that for a second time interval, that is for L upon 1 plus m upon capital M into v naught, that's when the first collision occurs, less than t less than. Now the second collision occurs the same time interval after this time, so I must basically double this, 2L upon 1 plus m upon capital M into v naught. So this is the time that the ball is traveling in the car frame from right to left in that picture, and at the end of that time interval the second collision will occur. So for this particular time interval, what's happening is the car, remember we are interested in the velocity of the car, so the velocity of the car for this particular time interval is plus m, it's moving in the rightward direction, into v naught upon capital M, rightward direction. So for the first time interval it was traveling leftward at a certain velocity. For the second time interval it's traveling rightward at the same velocity, and the magnitudes of the velocities are the same, but they are opposite in direction, and the time intervals are also the same. So it basically means that the car, it travels left first and then it travels right, and the displacement of the car finally is going to be equal to 0. That's when the second collision occurs. Now when the second collision occurs, the data suggests that the ball and the car have a perfectly inelastic collision, so it's going to stick. It's not going to stick, maybe it comes down, it slides down. So finally it is said that the car and the ball, that is the ball comes to rest relative to the car. That is what is suggested in the question. So the final situation is going to be this, you have the car over here, the fellow over here, and you have the ball, the ball is over here, ball is over here. So the ball and the car and the boy inside, they aren't moving with respect to each other. and they have the same velocity. All these three objects have the same velocity, but their total momentum must be equal to 0, because momentum, well, in the horizontal direction I'm saying, and because the momentum in the horizontal direction is conserved, so obviously each of these objects must have a velocity equal to 0 in this direction. So which would mean that the entire system is at rest at the end. So what happens is, the car, to begin with, it travels left at a certain speed. That speed, of course, you know that the speed is m v naught upon capital M. It travels that way, and for a time interval, already the time interval we have calculated, it's this time interval, so you can find out how far the car moves towards the left. And when the collision occurs with the right end, the car thereafter travels right for the same time interval, that is for L upon for this time interval, that is, and at the same speed but in the opposite direction. So you can find out the distance again. It's the same distance, it will travel towards the right, and when the ball collides with the left hand side end, and there is a perfectly inelastic collision and all that, the entire system comes to rest. So it means that the car comes back to its original position. So in all this, we have assumed that the ball, it travels straight like that, and that's not true in practice. What will happen is the ball goes this way, and maybe it will bounce, but you can work it out, because if you assume that the ball is projected horizontally as suggested in the question, the horizontal velocity component is not going to change with respect to time during the bouncing process, assuming that there is no friction between the floor and the ball. And even at this end, when we use the coefficient of restitution equation, it is the horizontal velocity of the ball which is going to be used in that equation, because that's the the formula is the coefficient of restitution is equal to the mod of the velocity of separation upon mod of velocity of approach, separation upon approach, and along the line of impact, and the line of impact is, in this case, is going to be in the horizontal direction. So the result will be valid even if the ball follows a bouncing sort of trajectory. So that's it. That's the explanation of the question and its solution.